Blood has always been in high demand, but with the supply constantly decreasing, shortages are becoming more and more frequent around the world. Especially because of COVID, the problem has worsened. Take our country of Taiwan. Blood supplies have been the lowest they've been in 20 years. Because of the lowering supplies, governments are incentivizing blood donations, and researchers are attempting to create synthetic blood. However, so far, there have been no successful implementations of blood products, and there are major ethical concerns with commercializing blood. What if there was a way to counteract this shortage? We are TAS Taipei, and we aim to increase the supply of universal donor blood through enzymatic conversion by cutting off antigens present on AB blood types.
We have identified 3 enzymes that act as molecular scissors to cleave off terminal sugars on A and B red blood cell surface antigens at distinct sites. The first is alpha-galactosidase, AGAL, to cleave B antigens, which are on type B red blood cells. The second is alpha-N-acetogalactosaminidase, NAGA, to cleave A antigens, which are on type A red blood cells. And the third is endo-beta-galactosidase, endo-beta-gal, to cleave both A and B antigens. The resulting antigen after cleavage is the H antigen, which the anti-A and anti-B antibodies cannot recognize, and thus does not elicit an immune response in the human body. To produce the 3 enzymes that cleave off the red blood cell antigens, we designed plasmid constructs to maximize the expression of these enzymes in BL21 E. coli strains. Through literature research, we designed open reading frame sequences for alpha-gal, NAGA, and endo-beta-gal. To express and purify our proteins, we attached 6X histidine tags through glycine serine linkers, a strong T7 promoter, and a double terminator. We successfully expressed and purified AGAL and NAGA enzymes. We then validated the function of these enzymes using colorimetric tests, thin layer chromatography, and mass spectroscopy. Our results show that the enzymes successfully cleaved their respective substrates and demonstrated specificity of the enzymes through the lack of enzyme activity on their non-specific substrate. To quantify enzyme activity, we performed reactions at various substrate concentrations and measured the absorbance at different time intervals to calculate Michaelis Menten constants for enzyme efficiency, which we used to design our convergent kit prototype. We also used thin layer chromatography. By comparing the RF values to the control values, our results show successful cleavage for alpha-gal. Finally, we further test the enzyme specificity by using A and B antigen trisaccharides as substrates for NAGA and alpha-gal respectively. After enzyme reaction, we use mass spectroscopy, a technique used to detect compounds based on molar mass, to determine the compounds present in the reaction solution. Cleavage was successful as shown in our mass spectrums, with peaks at 533 grams per mole for both alpha-gal and NAGA with their respective substrates. The culmination of results from all of these tests strongly demonstrates the functionality and specificity of our 3 enzymes.
With our enzyme experiments yielding promising results, we began designing a blood type conversion kit to bring our project into the real world. We developed a modular 2-step blood type conversion kit. In the first step, washed blood will be converted by enzymes. In the second step, converted blood will be purified and prepared for transfusion. We then developed a specific hardware to mediate the enzymatic conversion process in our kit. To evaluate various components of our prototype kit design, we performed a series of proof-of-concept tests with porcine red blood cells, which possess similar morphology and antigenic structures to human red blood cells. We tested the activity of NAGA using this agglutination theory. We added NAGA to red blood cells and then observed if agglutination would cease to occur when human anti-A serum was added. We found that enzyme-treated red blood cells did not form clumps and agglutinate, while PBS-treated red blood cells, our control, demonstrated visible clumps. Our results from this test firmly indicate the ability of our NAGA enzyme to cleave surface antigens on blood.
Through our experiments, human practices, and modeling, we have found a solution to the global blood shortage. This is our transfusion solution. This is Universo.